Now see here photoelectric effect. So see here we have seen here when the radiations of the suitable frequency is made to fall on the metal plate. If you have got a metal plate like this here and radiations of the suitable frequency, that is the minimum frequency required to emit the electron, that frequency is known as threshold frequency. So if the frequency of the incident radiation is equal to threshold frequency or greater than the threshold frequency, then the electrons are emitted here. So now the phenomenon of the emission of the electrons from the metal surface when radiations of the suitable frequency fall on these metal plates is known as photoelectric effect. So in the photoelectric effect, first main terminology is here, that is the threshold frequency, that is the minimum frequency required to make the electrons move out of the surface, and another one is here the work function we need, because the work function is equal to here h nu naught. So now we will study about the emission of these electrons and the photoelectric current. Now see here, this is the experimental study of photoelectric effect. In this thing is here, there is a glass tube is here that is evacuated, and now there is a plate C that is called emitter plate, and plate A is known as your collector plate. This side is here that is known as your commutator. By using commutator we can change the actually polarity of this plate A. Now there is a source of radiation here that we can say star, I have taken S. Now the radiations are coming from this side, this window, and falling on the emitter plate. If the frequency of the radiations are more than the threshold frequency, then electrons are emitted from this collector, this emitter plate. These electrons which are just emitted from this, they are on the surface of the metal, but if the frequency of the radiation is much more than the threshold frequency, they will come out of the surface. And now this plate, a collector plate is A is placed first positive, is kept at positive terminal, that is the positive potential is given. So these electrons move towards the collector plate. When these electrons move from C to A and reaches to here, the current flows in the circuit, that is known as photoelectric current, and this emission of the electrons from the metal plate is known as photoelectric emission here. Now what happened to the photoelectric current? If you are keeping the frequency of the radiation falling on this emitter plate C is constant and intensity is varied. When you are varying the intensity, you will find there is a relation between current and intensity. Here I will write here intensity, and here we can take photoelectric current, photoelectric current. So when the intensity of radiation is increased, keeping frequency constant, then it is found that photoelectric current increases linearly. It means the number of photoelectrons emitted per second depends on the intensity of the radiation falling on the metal plate C, that is on the emitter plate C. So first one is here the effect of intensity on the photoelectric current. Now see here, we have seen effect of intensity on photoelectric current. Now we will see the effect of potential of plate A on photoelectric current. Now what happens if you keep on increasing the potential of plate A, that is a collector plate. If you keep on increasing its potential, then what happens? These more and more electrons are being attracted by the plate A. After some time you will find all electrons will be reaching to the plate A. At this stage current will be maximum, and this is known as saturated current. So first the current attains its saturation value. Now what happens if you apply negative potential to the plate A with respect to the plate C, and this negative potential keeps on increasing. If you keep on increasing this negative potential, what happens? These electrons are being repelled, and at certain value no electron will be reaching to the plate A. At that condition, the maximum energy, kinetic energy of the electrons, that is half mv max square, is equal to EV naught. This V naught is here the minimum negative potential of the plate A, at which the photoelectric current becomes 0. It means the photoelectric current stops. At this stage no electrons are reaching to the plate A. So this potential is known as stopping potential, and then maximum kinetic energy of the electrons R is equal to this. But see here I have kept the frequency constant. intensity you can vary. So, now in this case you will be getting the graph, and the graph when will we draw. So, we can obtain in this manner. Here this I have taken here the photoelectric current, and here is the potential of plate A, and the graph you will be getting something like that. Here this is intensity I1, this is intensity I2, this one is your V naught. So, in the graph it is clear here, if you keep on increasing this potential of the plate A, current increases and it becomes saturated after some time for intensity I1, and if you increase the intensity, saturation value is larger, this value is larger. So, we can say here I2 is greater than I1, but when you keep on decreasing this potential and make it negative with respect to plate C, so at certain potential, that is V naught, no electrons are reaching to the plate A. At this condition, photoelectric current becomes 0, that is a V naught, and at the V naught no photoelectric current is obtained, and this V naught is known as stopping potential. But see here, by varying the intensity, we are getting the same stopping potential for the two radiation if the frequency kept constant. Now, see here effect of frequency here on the stopping potential. So, if you keep on changing the frequency, then you will get the graph like this. Here this is your potential of plate A, and here you are getting here the photoelectric current, and the graph is something like this here. So, you are getting here intensity is kept constant here. When the intensity is kept constant, the saturation value of the current remains constant. But if you see here the frequencies like a V naught 1, V naught 2, that is a V naught 3, these are the stopping potential. For these three radiations of the different frequencies, we can take nu 3, nu 2 and nu 1. Stopping potential is different. So, here nu 3 is greater than nu 2 is greater than nu 1. So, the value of the stopping potential depends on frequency here. So, the radiations of the different frequencies have different stopping potential provided intensity remains constant. We can also say intensity does not affect the stopping potential. So, now we have seen the variation of the stopping potential with the frequency. So, we can draw the graph also between stopping potential and frequency. So, we can write that, draw the graph in this way. Here we can take frequency, and here we can take a stopping potential, that is a V naught, and for this metal plate here we can write like this, and this, suppose this is metal plate A, metal plate B, and this is here actually the threshold frequency here. This is 1, nu 1 and nu 2. So, stopping potential actually is directly proportional to the frequency of the radiation. Now, say we have done the experimental study of photoelectric effect, and we have seen all the factors which are affecting the photoelectric current or stopping potential. That is actually called also the laws of photoelectric emission. First point was there here, for the given photosensitive material, photoelectric current is directly proportional to the intensity of radiation falling on this, provided frequency kept constant. Second one was there here, the emission of the electrons take place at the certain minimum frequency, and this minimum frequency for the given metal plate is known as threshold frequency. Above the threshold frequency, stopping potential is directly proportional to the frequency of the radiation falling on the metal plate, but it is independent of the intensity. Now, the stopping potential here, and if the intensity is varying, suppose, and frequency remains constant, stopping potential remains constant. And also this photoelectric emission is an instantaneous process. It means there is no time lag. As soon as the radiation falls, we get photoelectric current. Now, say the next topic is here Einstein's photoelectric equation. We have done photoelectric effect, and in photoelectric effect we have seen when the light radiations fall on metal plate and electrons are emitted, as a result we get current, that is called photoelectric current. Now see here, light radiations consist of small packets, this is tiny packets of energy, and these packets of energy known as quanta. And each quanta is known as, and that means each packet of energy is referred as quanta, and these are known as actually photons. Photons has got the rest mass 0 and charge is 0. These photon travels with the speed of light in vacuum, or that is in a free space. Speed is here, that is 3 into 10 raised to power 8 meter per second. So light energy coming from the sun is considered to be in the form of the photons. When these photons, or when this light energy falls on the metal surface, electrons are emitted. So according to Einstein, when the energy, that is E is equal to h nu, that is energy of the photon, when this energy falls on the metal plate, this energy is spent in two ways. First one, to make the electron just come out of the surface, that is means equal to the work function, and second part of energy is required to provide maximum kinetic energy. So we can write according to Einstein's, that is E is equal to work function plus maximum kinetic energy. That we can write h nu is equal to phi naught plus half, that is kinetic energy here max. So we can write kinetic energy max is equal to h nu minus phi naught. We can also write h nu minus h nu naught, or we can write h into nu minus nu naught. So nu naught is known as here threshold frequency and nu is the frequency. So this is Einstein's photoelectric equation. Now see here, we can justify all laws of the photoelectric emission by using this equation. Since one photon emit or eject one electron, so when the number of photons falling on the metal surface are increased, more number of electrons are ejected. It means that is when the intensity is increased, photoelectric current increases. That is actually here the first law of photoelectric emission. Second point I can take here, if you are taking nu is greater than nu naught, if nu is greater than nu naught, then the kinetic energy is positive. It means kinetic energy varies linearly when the frequency of incident radiation is increased. Second point we can take, if you are taking suppose nu is less than nu naught, when the nu is less than nu naught, kinetic energy will be negative, which is impossible. It means no emission of the photoelectron takes place if the frequency of falling radiations are less than the threshold frequency. So this is the third law of the photoelectric emission. Now the fourth one is here, as the photon falls on the metal surface, elastic collision takes place and suddenly energy is transferred to the electrons. As a result, electrons come out of the surface. In this process, there is no time lag at all. It means there is no time gap in this case. So as photon falls, electrons are emitted, and also we know it, photoelectric emission is instantaneous process. So this is the the last law of the photoelectric emission. So you can explain all laws of the photoelectric emission by using Einstein's photoelectric equation.